Good afternoon, everybody. Many thanks for joining us today for our tech talk. Today's tech talk is about beam strengthening. I'm Steve Musa, one of the operations team, and I'm joined by our technical director, Jayesh Nambona. Good afternoon, Jay.
Good afternoon.
So we're here to talk about beam strengthening provisionally in detail. First thing I just want to do is just run through what we're our itinerary, why we use carbon fibre, beam strengthening itself in a bit more detail, with some projects to look at, and then any questions, which will be after about 20 minutes. So why use carbon fibre? It's a general question, Jay. What are the points? Why would the client look at using carbon fibre as opposed to traditional concrete and steel?
Yes, so carbon fibre strengthening becoming quite popular these days. Mainly it's called CFRP strengthening, or carbon fibre reinforced polymer strengthening. The reason for that is that carbon fibre is very high strength and lightweight material, which is used for strengthening structure by applying reinforcement from the outside. That's why it's called externally bonded reinforcement. And if I just give you an example in terms of number, carbon fibre is at least 3 to 4 times stronger than steel and at least 7 to 8 times lighter than steel. So you could see strength to weight ratio and why people prefer to use FRP over traditional methods. And that is the reason it is becoming quite popular. And the other advantage is that it can be used on concrete, steel, wrought iron, cast iron, even on timber structures. So there are pretty much all types of structural material which can be strengthened using carbon fibre.
And it's a bit of a misconception that a lot of people think it's a sort of relatively new system to use, and it's not.
It's not completely new technology. This was first used in aerospace engineering in 1944. Then I think it was used to make aeroplanes, fiber boats, motor cars, and then in 1988 this was first used in construction. So it's pretty much, at least I'd say 35, 37 years old technique. So it's not that new, but as compared to concrete and steel, it is still a new technology. And that's why some people think that it's a new material and new technology, and not many people are aware of it.
Right. I know one of the areas that we're looking at, and we're seeing more and more, not just designers but main contractors, because they're looking at the economies of scale, and they can save money.
Yes, so carbon fibre is a very economical solution, but if you see the cost in terms of the whole cost, if you just compare the cost of the material only with carbon fibre with like steel or concrete, some people will find it expensive, but we all know in construction it's not just the cost of material, there is a cost to put that material in place and everything. So in that instance, carbon fibre becomes much more economical because it's very lightweight material. So you don't need big wagons or cranes to put it in place. And the strengthening by carbon fibre is much quicker as compared to any other traditional method. And the other advantage of using carbon fibre is that it is very low profile material. So the typical thickness is around 1 millimeter. So imagine if you're able to strengthen a beam, column or a slab with one layer of carbon fibre, it means you're increasing its dimension by just 1 millimeter. And that is the reason architects also prefer to use it.
I think we can show that in some of the projects that we'll be looking at a little bit later on in the tech talk. So it's if we're looking now specifically at, as I say, it's the beam strengthening side as an asset. So when you're looking at beam strengthening, what are the key areas?
Yeah, so beam strengthening is one of the most common types of strengthening which is done using carbon fibre. And generally beam strengthening is done, it's a flexural element. So mainly the reason for strengthening a beam is probably the flexural requirement, so you can strengthen it for increased sagging moments or increased hogging moments, and also beams are also strengthened for shear. So on our screen we can see a very simple schematic which shows where the carbon fibre is applied. Carbon fibre has very good properties in tension, so it is always recommended to be applied onto the tensile face of structure. So in that image we could see that carbon fibre is applied at the underside in the mid-span. That is to improve the sagging moments or positive moments, and on top near the supports to improve the hogging moment resistance. But in top strengthening as well, there is a very important construction detail which people miss out. So what they do is that generally they take the strengthening up to the ends and supports and stop it there. Now if you're stopping the strengthening at the key area where you have the peak stresses, because that's the location where we are going to have the peak stress, if you're stopping the FRP there without any anchorage length or development length, the FRP will not be effective there. So technically you should have some sort of anchorage detail or end detail in those zones, and then the strengthening will become effective. So for that reason you need to pay attention to the end details in those kind of situations. And similarly, for shear strengthening, if we can imagine putting like a link or a stirrup from the outside of a beam.
Okay.
So that's why this strengthening is also known as U-wrap strengthening, because it is done in U shape, as you could see in the images. And again, the same sort of anchors can be used to anchor the FRP into the beams or slab to get the full effect as in closed loop.
So basically, just to reinforce that, if they're not anchored on the span at the end, it's not worth doing them.
Well, it's not be effective there. So it will be effective few 100 millimeter inside, accounting for those anchorage lengths. But we all know we are doing strengthening for that particular location, so it needs to be anchored beyond that point.
I think we've got a bit more detail on that. I think on the next slide, I think you go into it in some more depth.
Yeah, so this is the slide which shows the anchors which we were talking about, that how these anchors are used. So generally there are two types of anchors. So one is called nominal anchors, which are small anchors. They are used for mostly construction detailing rather than an actual force transfer kind of situation. So they are very small anchors. So how they are used, we could see in the simple 3D schematic that a hole is drilled in the concrete. We saturate the anchor, put half of that anchor into drilled hole, which is filled with epoxy, and splay the remaining half onto the face of the element. Then we'll put another layer on top of it, so it will become one unit which will cure simultaneously, but is actually going into concrete. So it provides you additional anchorage or bond capacity, so debonding and delamination failure will not happen. So that's how these nominal anchors are used.
Okay.
But then we also have these bigger anchors, which you could see the person holding in his hand. They are called super anchors. So they are nothing but just specially designed anchors. They're similar to the the nominal anchors, but they are much bigger and denser in terms of fabric density and all. They're designed for a particular force. So the situation where we use them is shown in the images, like if you see on the bottom left there. This is a situation where we did the slab strengthening for hogging moments. And again, as I explained in the previous slide, that we need to anchor the FRP in the location there near the ends. So in this situation, there was a column in the way. So what we did was that we drilled hole through the column, use these bigger anchors, pass them through the drilled holes, play them on both sides like a dovetail, put one more layer on top of it. So after curing, these anchors become as a tie, which is transferring force from one side to another side. And that's how we did that kind of strengthening. So now we can say that that is particularly the top reinforcement in that location, which is continuous in that location. It's not stopped at the column face. So that's how these bigger anchors are used. The other example of them could be using them in the shear core or shear wall situation, where you have to strengthen an element vertically, but you have slabs breaking that pattern. So in that situation, you'll drill hole through the slab, use these bigger anchors, pass them through the floor above to floor below to transfer this strengthening from floor above to floor below. So that's how these anchors are used.
So the picture in the central one with the guy holding the anchor, those are specially designed by our own team?
Yes, they are specially designed by us. We know the forces which we need to carry, and depending on those forces, the number of anchors, the diameter of anchors, the length of them, everything will be designed.
Okay. So we're going to talk about some of the projects that we've worked on quite recently in the UK, which particularly looking at the beam strengthening side, yeah?
Yes, so the first project we're going to talk about is the beam strengthening in Selfridges on Oxford Street in London. So again, it's one of the buildings owned by Selfridges. It's not the actual store which needed strengthening, but they were changing the use of the structure, which is very common these days. You've got an existing structure, you want to add additional stories on top of it, or convert that particular structure from commercial to residential or vice versa. In those situations, the strengthening may be required. So that was same thing happening there. They were adding additional stories on top of this 6-story structure, and the new steel columns were going right on top of the existing beams, which was generating the point loads, and they had to strengthen the beams for additional moments and shear forces. So FRP was chosen there. The reason for that is the main reason was headroom, because if you go with the steel solution, you will reduce the headroom, which is not advisable, especially in those kind of situation where you already got a low headroom kind of situation. So FRP was preferred there. So we strengthened these beams by applying FRP at the underside for sagging moments, also on top, which we could see the bottom left image. So that's the strengthening on top of the beam or on top of the slab. And the anchors are shown there. So they were applied to justify a check in TR55 design, which was for shear crack induced FRP separation. So to justify that check, if that check fails, which means you need to confine the FRP, Confinement at the underside is quite simple. You can put another layer of U-wrap to confine that FRP, but on top it's very difficult because you've got a slab there. So in that instance, we use the anchors as we explained on the previous slide. We drilled hole through the slab, gone onto the web of the beam, and then applied the anchor all the way through. So that's how we applied a hoop there to confine the FRP. So that's how these anchors were used.
I think just going back to the, we're saying about the headroom and with carbon fibre so thin, architects really do prefer using it because they can save a lot of space.
It is, yeah. So in that particular project as well, architect was very keen to use carbon fibre because the other solution was to put new steel beams underneath, which was, as I said, reducing the headroom, changing the profile completely and everything, and also adding dead load onto the structure, which was becoming difficult for structural engineer. So for that reason, FRP was preferred.
Okay. So another project that we've looked at, I know this actually won an award, the LSBU at London South Bank University. A strange design for this, but again, carbon fibre was obviously the go-to solution.
Yeah, so this is, as you said, it's London South Bank University, so it's a very big structure near Elephant and Castle underground station. The reason for that strengthening was that they were changing the university's, existing layout and everything. So they're changing the position of library, introducing new features, TEC, or introducing new sports facility and all those things. So there was a lot of work going on. The reason for strengthening was that this is a typical 1960s waffle floor construction. So they have the ribs running in both direction, but for some strange reason there was very minimum or no reinforcement in the transverse ribs. So for that reason they were treated as one-way spanning T-beams in a series. So we strengthened them at the underside by applying a plate, carbon fiber plate system. The reason we use the plate there is that because the ribs were only 100 millimeter wide. So if we cut the fabric in that width, we may end up with a lot of waste. So for that reason, a plate was used, which was 100 millimeter wide off the shelf. So we applied plate at the underside. We did do the shear strengthening by putting a U-wrap, as we could see in individual waffles. And then we also applied FRP on top of these ribs to strengthen them for hogging moments. So all three types of strengthening was done there, as we do in the beams. And also the primary beams were strengthened for flexure and shear as well. So this was a very big project, and as the reason why it won the award was that, as I said, that generally our standard size projects were like 1,000 or 2,000 meters square of carbon fiber, but on this particular project we used 8,000 meters square of carbon fiber with 12,000 shear anchors, because there were lots of waffles we had to strengthen for shear. Also fire protection system was applied on top of it as well. So it was a massive project. The reason for the award was that it's actually the structural engineer who won an award from iStructT on this, and that was in the sustainability category. The reason for that is that by using CFRP, the CO2 emission on this particular project was just 49 kg CO2 per meter square, as compared to 105 kg CO2 per meter square emission LETI target of 2030. So they managed to do it now, and for that reason they won the award. And the 3D image shows the amount of steel and everything still used there, even after using that much carbon fiber. And that also reduced the CO2 emission there. So for that reason it won the award.
If people want more information, I believe there is a report on the iStructT website, yeah? Yeah,
it is available on internet. If you search London South Bank University, you'll find many reports on it. But on iStructT website, there is a paper on sustainability which shows all the calculations and everything, that how they calculated that kind of CO2 and all those things.
I think what we're going to look at now, and I think a lot of people understand that the design is important, but also the design married up with the preparation and application of carbon fibre is quite critical, yeah?
Yeah, so this is another type of strengthening, which is also a beam strengthening, but this is done for new service risers penetrations through the beam. So again, the same design concept there. This was mainly strengthened for shear. So first thing we do is surface preparation, which you've seen them doing by diamond grinding. Then they have to clean the area by vacuum so that it becomes dust free. They have to drill holes for the anchors, make them, clean them as well and everything. Then there is a QA, QC check. They have to measure the temperatures, humidity and all those things to make sure that this is the correct environment to apply FRP. Then they do priming, which is done using pure epoxy. Once priming is done, they apply the first coat of thickened epoxy, which you could see the white color stuff they are applying. And then once they have applied that coat, they'll use the first or unroll the first layer of carbon fiber there. Now the carbon fiber this guy is applying is actually saturated in a different area on same side. So when he's applying it in this place, it is in wet condition. That's why this application is called wet layup method. And generally, whenever we are using fabric type of material for strengthening structure, the application needs to be wet layup method. There are still people out there who do dry layup. So in dry layup, what you'll do, you just prime the area with the epoxy. You put dry fiber on top of it and try and patch that fiber on that saturated or primed area, and then put another coat of epoxy on the dry fiber. In doing so, nobody can guarantee that 100% resin impregnation through each and every fiber. That's why that dryness could lead to or may lead to a debonding or delamination failure. For that reason, dry layup is more or less abandoned now. So it needs to be done as wet layup. So that's how we apply FRP. We apply first coat, then this guy's inserted the carbon fiber anchors, splay them, put another coat of epoxy, then another layer of FRP, and that's how you build up the number of layers. So once you applied the required number of layers, you'll have to let it cure. Generally in ambient condition, it will be cured in 72 hours or 3 days, which means you can reload your structure back to its new capacity in 3 days. In this instance, they were able to cut the core through the beam in 3 days' time, which is the quickest way to strengthen any structure.
So that's it. That's the presentation, our tech talk today on beam strengthening. If you have any questions, please drop us a line, drop us an email, and we will get back to you. Many thanks for joining us today. Hopefully we'll be working with you soon.